is the due date of the homework assignment, right?
Yeah.
Yep.
Okay, so what I'll do is we'll talk about the homework assignment first. Not sure how many people got it done in time, but as a general thing, I always talk about the homework assignment on the due date so that you guys know the solution. So especially for people who could not get it done completely or got it done but really don't understand how they got it done, I mean, it's possible. I mean, that someone can get something done without completely understanding, how it works. So that's what we'll do today, is to just look at this homework assignment first. And when we have time, we're going to move on to talk about file operations or system services. Okay, how does your program interact with the operating system? Okay, because it is great that we now know how to write not subroutines, but control structures and make use of all the addressing modes and whatnot, and we can make useful programs already. But if you cannot interact with the operating system, you're still missing out a whole lot. In other words, how do you read a file? How do you write to a file? Okay. Now, when I say a file, it is not just a regular file that we understand like, oh, here's a folder, it has a file inside, and we can open the file, and this is the content of the file. We are talking about files in general, standard in, standard out in C and C++. Okay. How many people still remember standard in and standard out in C++? Okay. Was that an exciting thing?
Yes.
Not really, right? I mean, it's good. Okay, we got 2 conveyor belts, right? One coming into the program, one going out of the program. That's about it. But guess what? Those streams, or those quote-unquote files, is the basis of just about anything in programming, especially in a server-client type of situation. Okay, because a socket is a file, but a socket is the concept that allows your web servers to serve multiple connections at the same time. So that's useful concepts, but first of all, we'll get this program done first. So this is called string and copy, which resembles the actual subroutine in C and C++. Okay, it does exactly what that subroutine is supposed to do, except now we are doing it in assembly. So we'll go ahead and do this homework assignment. And even if you have done it already and you know, okay, I got it done and I know my program works just fine, we may still be able to talk about it. I may learn something from your solution. So we'll go ahead and take a look at this homework assignment first. All right. So this part, I don't want you guys to make any changes. For testing purposes, obviously, you can change your max length to 3 or 4, just so that it is easier to test your program, so you don't have to fill up all 32 bytes with non-null characters just to test your program, okay? But when you turn in your program, when you turn in your homework assignment, you have to make sure that it is the same way as it is now, just so that my script can set up all the test conditions without having to worry about this part. And then we move on to line 11. Use man string and compare to look up the official description of string and compare. So if you want to understand what the algorithm is actually trying to do, this is useful. Okay, looking up the man page is useful because you have a secondary source of description of what string and compare is supposed to do. But for people who don't really care, it's already the C code. The C code is already here, starting from here and all the way up to here. Okay. That's the C code, and with the C code, you can just do a translation and make sure that in the translation nothing get lost, and the program will still work, even though if you don't understand what string and compare is really about. Are there any questions up to this point? Okay, there are no questions. So what we'll do is we'll start to flatten the program first. Okay, so I have a place for you to insert your code to perform string and compare, and do not modify anything before, do not modify anything after. And I want to make sure that EBX is our return value, quote-unquote return value. It will get a value of 0 if the 2 strings are considered the same. It has a value of 1 if string 1 is greater than string 2, and a negative 1 if string 1 is less than string 2. But over here, this is the conditional statement that will kind of determine which one is smaller than which other one. All right, so we'll go ahead and start with this program. The first thing I would do is to take this code and translate that back into an actual C program. Surround the pseudocode with main, and actually test the program, test the pseudocode in C and C++ first. Okay, that was the recommendation, so that you can actually flatten the program step by step and make sure that in the process of flattening, you're not changing the meaning of the program. How many people did sort of something like that? Maybe not exactly, but started off with a C program first. Was it helpful, or it was okay? Okay. Because it seems like a waste of time. It's like, why do I want to bother with a C program first and then come back and do it in assembly? Well, because it's easier to debug when you're dealing with C and C++, and in terms of just the logic. And when you translate into assembly, it should be more or less mechanical by that time. All right, so what I'll do is I'm going to do an in-place translation here. And since my own note says, insert your code here to perform string and compare, I'm going to copy line 18 up to line 31 to here. So 18 to 31, copy to this point. So this way I'm still, following my own instruction, not, putting any code before or after the 2 lines of comment. Okay, so here we have the first one to translate, and we'll have to flatten it. So the first step to flatten a while loop is to look for the negation of the condition. Oops. And make it go to the end of this while loop here. So we have to label end while all the way down here, and somehow implement the negation of the condition so that we can branch around the block of code in the inside. In this case, we have a big, huge conjunction and with a negation on the outside. So you can go through one of 2 processes to get this done. You can either just kind of mechanically and blindly translate the negation into the control structure to deal with negation, or you can use De Morgan's law and turn this whole thing into a disjunction. Or you can just intuitively understand and say that, oh, okay, so if any one of those conditions, L, whatever P1 points to equals to whatever P2 points to, and whatever P1 points to is non-null, if any one of those conditions is not met, it's time to get out of the loop. So intuitively, you can also turn this into a disjunction and just say that I'm looking for the negation of each component of the conjunction to get out of the loop. So either way works, okay? So you can use whatever way you want to look at this and say, so I would just use that way and say that, okay, this is the first reason to get out of the loop. Why, not L, which means L is 0. This is my second reason to get out of the loop. If the first one is not met, this is the second reason to get out of the loop. And here's the third reason to get out of the loop. Is that part okay? Yep, good. Okay, good. Now we can look at each one and say that, oh, okay, so it's not really such a big, long condition anymore. It will be helpful if we look at it this way, right? Because not L is basically saying, okay, the negation of L, but the negation of L is basically saying if L equals to 0, then the negation becomes true, which also means we are just making sure that L does equal to 0. If that is the case, go to end while. All right. This one is, the way it is, it's already a comparison, no issue over there. But this one will turn it into a comparison as well. But this one is not looking for the negation, so we are basically asking whether the byte that is pointed to by P1, is it not a null byte? If it is...
Shouldn't it be the other way?
It should be the other way. I did the translation wrong the first time. So that should be a negation here, and this one should be a negation here, and that should be a negation here.
The other one's right.
That one's right. Oh, because of the not L. I forgot to negate the other two. Okay, so there we go. We translate that. There we go. Okay, so now we can continue with our translation. This one becomes, a single comparison followed by a goto, which means we can use the general template of j something. This is a conditional branch. Compare first. Okay, this is a compare with some kind of width. We'll specify the width later. The 0 as a constant has to go first because only the first operand of a compare operation can be an immediate operand. You do not want to use a direct operand in this case. You want to use an immediate operand. So we are comparing 0 to L, and now you have to say, okay, how do we keep track of L, which is the length that we're comparing? Well, there are several ways to do it. The first way is just to use a register to do this. Okay. The second way is to allocate memory, like a 32-bit chunk of memory, and call it L. If you use memory to do this, it's easy in a way, but you have to know how to use the direct operand. That makes it a lot easier. If you do not know how to use the direct operand, it makes it harder. So do you guys want me to use the direct operand or not?
Yeah.
Is that okay? All right. So using the direct operand, I'm going to have to allocate storage for L. Did I allocate anything like that up here? No, I do not. Okay. Now, since I did not allocate anything for L, now there's a trick that you can do something like this. You can actually switch to the data section and define the label L and allocate .int 0 in the data section, and then turn it back into the .text section. In other words, in your program, you can interleave code and specification between the two sections any way you want to. It's basically the same thing as trying to write into two different books. And .data is basically saying, oh, let's switch to the data book. And .text means let's switch to the instruction book. So, but each book has its own bookmark to mark the next available page. So you can do all the switching that you want, but it will still be contiguous as far as .text is concerned, and also as far as .data is concerned. So this is one little thing that you can do to allocate, a space to put something without interfering with anything else. So that's one way to do it. The other way to do it is to use one of the registers to do it, okay, which is also fine. Do you guys want me to do it that way too, or not? Use a register. Use this one.
Can you do it this way? Because I did it the register way. I'd be interested to see you do it this way.
Well, doing it this way is not. It simply means that you can use L as a direct operand.
Okay, so you just put that there.
Yeah.
Okay, never mind.
The problem with using registers is because you only have like 4 or 5 really general purpose registers, and once you use them up, you're out of resources, right? Using this approach, gives you a lot more space to play with because you just have to allocate, another 32-bit chunk and call it a certain label, and then you can use it. For most things, you cannot do an directly with anything that's already in memory. So you have to put it into a register first and then do the indirect access. So it's not as handy as registers in some way, but at the same time, you only have so many registers to play with. Yep.
So can you move values into L now if you wanted to?
You can move values into L, which means before the loop, you have to initialize it, right? So then you have to say L, okay, L should start with the entire length of the string. So as such, you can use a move L 32 as an immediate operand into L. So that will work, assuming L is allocated this way. But it doesn't have to be this way. I think we have enough registers, because we have 2 registers for the pointers, P1 and P2, 1 register for L. So we have 1 left over for the character to be compared, or the character to be moved as a temporary register. So even without the use of L as as allocated this way, we can still make this program work. So which way do you guys want me? Yeah, go ahead.
I was just wondering if we could use .byte instead, because we don't really need a 32-bit.
You can use .byte. Definitely, you can use .byte. When you use .byte, you just have to make sure that this becomes B, and you change all the operations to a byte-wide operation. So that will work as well. Yeah. It's not any faster because we are dealing with a 32-bit processor here. So the ALU already has a 32-bit width, and it can process a 32-bit integer at a time. And when you tell it not to use the other 24 bits, it's not any faster because it's still going through the same calculation. But you are saving, quote unquote, you're saving memory in this case, even though it's only 3 bytes out of, you know, whatever gigabytes we have available, right? All right. So we have to kind of take a vote here. Do you want me to use L like the way it is, or do you want me to use a register instead of L?
This is a register.
Do it as a register? I think we can do it as a register first because that's actually in a way, it's an easier approach. Okay. So to switch it to a register, we have to kind of state which register we want to use for L. So I just randomly say that you'll use EAX as the length, which is L. So from here on, you know, it becomes EAX. And once again, I don't really need 32-bit. I could have just used AL, you know, for the purpose of counting. That would still be okay. That would free up AH, you know, for something else. So we can do it that way. So let's do it that way and just use the minimum. Use AL as L. So now we use move byte AL. And we get rid of this one here. There's no need to use it anymore, so that's why I got rid of it. So every time we want to compare to L, we're using AL instead. And since we're just comparing to 0, and the answer is either equal or not equal. In this case, you know, if it is equal, we use a JZ instruction and go to the label end while, because it is time to get out when we have no more bytes to compare. And that's the end of the string end compare, which is length delimited. Okay, we specify we only want to compare up to a certain number of bytes, in this case up to 32, because, you know, max length can only be 32. Any questions about line 44 and line 45 and how that is implementing the quote unquote pseudo C code on line 43?
Then it needs to be you need to specify the width of the comparison.
Correct. Yeah, that's just a general template, you know, a placeholder for the actual thing to compare. Okay, now we can deal with this one. This one is a little bit more complicated because what we really want to do is to say compare byte whatever I'll pick ECX and EDX in this case. So we are now comparing whatever ECX points to whatever EDX points to. So as initialization, we have to initialize both of those things. And this time we have to use $str1 to go to ECX. And the comment is ECX is P1. And then we use the other one, EDX is P2. So when we want to compare what the pointers are pointing at, we have to use the indirect operand, because the indirect operand is the dereference operation in assembly language. Okay? So this is what we want to do. Okay, and it is also important to use compare byte, and in this case we say JNZ to end while, because the comparison specifies when they are not the same, we want to get out of the loop. Okay, and that's because, you know, when they are the same, we want to stay in the loop. So that's why we negate the condition and say when they're not the same, we want to get out of the loop. But this is not allowed. If you try to assemble a program like this, the assembler will come back and complain and say that on line 49, the opcode is now specifying more than one memory operand, because you can only have up to one memory operand. So this is why we need the other temporary register, just so that we can, you know, deal with something like this. So the trick to get around this one, which I demonstrated in the previous class, is to move one of these into a temporary register. Since we use AL for the counting purposes, we can now use AH for, you know, this particular temporary value, and then we just use AH in place of ECX indirect for the comparison. The other part that is also very important is the compare byte instruction here. If you use compare long or compare word, then you'll be comparing more than just one byte, which may or may not work. Okay, it depends on, you know, what strings you're comparing. For certain strings, yes, you know, even if you use the wrong compare with, it will still kind of work, but it depends on how the string itself is initialized. Right. So now that we have, you know, this part, you know, initialized and done, we can move on to the next one. The next one is this one here. Okay, if whatever P1 points to is 0, which means we have hit the end of not one string but both strings. Okay, so how do we know that at this point when whatever P1 points to is a 0, we have hit the end of both strings? Both strings have ended. How do we know that? How did we get to this point? Go ahead.
Well, you compared both strings before, and if both strings are equal, then and only then will you actually hit that bit of code.
Exactly, because if the strings are different, I would have branched to end while already. So the fact that I'm on line 54 means that the strings are equal up to this point. P1 and P2, they point to different bytes, but those bytes have the same value. Okay, so at this point I just have to say, okay, is whatever P1 points to a null, and if you want to use something that we already have initialized, which is AH, you can certainly do so here. So in this case, we just have to compare AH, which is already loaded with P1 in this case. Whatever P1 points to is already loaded with that byte. So we just need to compare that byte to 0. And if it is 0, which is a null terminator at a string, we can also now go to end while because the compare is now official again. So that's how we deal with the beginning part of the loop, and now we just have to deal with the body of the loop. The body of the loop is just adding 1 to the pointer itself. Now remember, there's no dereferencing here. Okay, we are not adding 1 to what the pointer points to. We're just adding 1 to the pointer itself. And which one is our P1 pointer? ECX. Yeah, so we are now adding 1 just to ECX. There's no indirect here because we are not interested at all at this point of what ECX points to. We are only incrementing the pointer, so now it's ready to point to the next location for the comparison operation. So this one is, whoops. So the other one is about the same, except we are using EDX, for the purpose of P2. And our length is AL, so we have to subtract byte. Remember, this is a byte-wide operation. Yep, go ahead.
Could you do add byte to CL?
So
when I tried compiling, it complained about something.
Okay.
And I changed it to CL.
Okay. Your question is actually 2 questions in one. Okay. The first question is, why is it complaining? And 2, if I do make it work with CL, would it work in general? Okay. So let me answer the first question first. So the first question is, I'm just going to copy and paste this line so I can do this without having to deal with the other one. Okay, so if you only use CL for counting purposes, this is not going to work because the width of the opcode, which is add-long, does not agree with its operand, which is CL. CL is an 8-bit register, but add-long says we want to do things in a 32-bit way, so they're not consistent. And that's why the assembler complains. It's like, okay, you specify 32-bit here, but then you specify 8-bit here. They do not agree. Okay, so you can fix it in 2 ways. You can make the register 32-bit, like what I have here, or you can change the width of the operation and make it an add byte. Now, if you change it to add byte, the program may seem to work for some cases. It will only work if the pointer is not crossing that FF to 0, 0 boundary. Okay, because a pointer is basically just an integer, right? It's just an integer that points to a particular location in memory. But it is a number. It's a 32-bit number. An address is a 32-bit thing. So when you increment, let's say it's already something, FF. Okay, FF in hexadecimal is 255 in decimal. Okay, you add 1 to it. Okay, if you do an add long, then the addition will have a carry to bit 8 of the 32-bit number and will propagate the carry bit throughout bit 8 to bit 31 with an add long. With an add byte, it will still give you a carry bit because adding 1 to 255 will yield a carry, but the result will be 0, 0. But that carry is now just tossed away because we are not paying attention to the carry. So as a result, if you use an add byte here, and it just so happens that the address is crossing a 256 byte boundary, then it won't work because it will go back to point to the beginning of the same page again instead of going to the first byte of the next page. Is that okay?
Yeah, but I think I did it this way.
Okay.
So I don't know.
So it depends on how memory is allocated. That would be something difficult to test too, because it depends on what kind of variable you allocate and the order of the allocation, because it depends on whether you push string 1 all the way to the boundary between two 256 byte pages. Do you guys see what I mean by this? Okay, if you look at memory itself and consider as big chunks like 256 byte chunks, let's assume this is the beginning of string 1, and let's just say that 32 bytes will cross over the 256 byte boundary here. So when the pointer points to the last byte before it crosses the boundary and you add 1 to it, with an add long it will go to here. But with a add byte, it will go all the way back to the beginning of the same page, because the carry is not used to change bit 8 to bit 31. Is that part okay or not? Okay. So that's why line 59 is dangerous, not only because it causes problem, it's also because it depends on how memory is allocated. In other words, you can have this code working for a long time, but because you're putting more stuff ahead of string 1, it pushes string 1 to this boundary, and then the program starts not to work. So that's why this is kind of a particularly kind of nasty issue, because it will delay the detection of the bug, and you might think everything is working. So when the program starts not to work, the natural thinking is, oh, it must be some of the new code that I added to the program, but it wasn't. It's not that case. It's actually something that was already here from the beginning, but since you're pushing the boundary to this point, then the symptom happens. So I'm gonna remove that line over here. AL can use a subtract byte in this case because we only allocate 8 bits for the count here. And at the end of a while loop, we also want to jump to the beginning of it. So now we have to jump to a begin while label. And that will just be the beginning of the entire while loop, which is all the way over here. So begin while goes all the way over here. And I think that should do it. And now we have the conditional statement to deal with. So we'll go ahead and deal with the conditional statement. Now with a multi-branch conditional statement, it's not really that much different from a like just a 2-branch conditional statement. We want to basically look for the negation of this condition. So we just basically say, okay, let's translate and flatten this by saying, okay, let's look for the negation of this. And if the negation is true, then we want to go to the else if branch. The else if branch is all the way down here. This is our else if branch here. And at the end of the first branch, we also need an unconditional branch to go to the end of the entire conditional statement, because otherwise it will fall through to the second branch without this particular unconditional branch. So we have an end if branch all the way down here to mark the end of the entire conditional statement. Okay, so now we look at the second branch of the multi-branch conditional statement and say, all right, we look for the negation of this. So else, the negation of this, I'm just going to do it, I'm going to skip one step. So I just say, okay, let's change the comparison to become the negation of the original condition. So if that is true, we want to go to the else label. The else label is going to be defined here. But before we go to that label, we also need an unconditional branch to go to end if, so that the second branch does not fall through to the else branch. Are we doing okay so far with the control structure overall speaking? Okay. And now we are ready to go back to this one here and say, okay, now how do we do this? This looks kind of nasty because it has got a negation on the outside, it's got a disjunction in the inside, and then comparison all the way in. You can also apply the Morgan's law in this case, because you can apply the Morgan's law apply the negation to the inside stuff, and then change the disjunction into a conjunction. So that's one way to do it. Right. So that eventually, okay, I'll just do it step by step in this case. So we'll apply De Morgan's law, and after you apply De Morgan's law and clean it up a little bit, then we're looking for L not equal to 0, and P1, whatever P1 points to does not equal to whatever P2 points to. So I'm really combining two steps into one. I'm combining the application of De Morgan's law as well as using the changing of the comparison operators to deal with the negation. So I'm combining those two steps into one. Okay, but let's just look at this for a little bit and see if it makes sense. If it is not the case that L equals to 0, or whatever P1 points to is the same as whatever P2 points to, then we want to go to else if. Is that really saying the same thing as if L does not equal 0, and whatever P1 points to does not equal to whatever P2 points to, go to else if? Are they really meaning the same thing? I mean, intuitively speaking. Did I explain De Morgan's law last time? I think I did. Did I apply it to an OR in the inside? Okay. So this is exactly like that. So once we have this, we can now do one more translation and basically get rid of the conjunction. When you have a conjunction, you have to basically say, okay, let's look for the negation of the first condition, because if L does equal to 0, we want to branch to the label that is going to fall through with this code here. So we'll say, if L does equal to 0, do not go to else if, just go to a continuation point here. So I'll just call it the continuation point of the if, and the continuation point of the if is going to be defined here. And then after that, we will look for the second condition, but without the negation. Then we will say, okay, assuming that L does not equal to 0, let's now go ahead and check whether whatever P1 points to is actually different from whatever P2 points to. If that is the case, then we go to else if. Is that making any sense? Okay. So now we can now go back to this one, because now it is just a comparison and a branch. So now we can say it is some kind of compare instruction involving 0 and A and L, but since L is actually our register AL, we'll compare register AL to 0. If they are the same, we go to the label called if continue. All right? If that is not the case, then we look for the negation of, then we look for this particular condition and go to else if. So once again, we are comparing, oh, I need to specify the width here. And by the way, this width here does not need to be specified. If you just leave it the way it is on line 73, the assembler automatically will pick compare byte, because the instruction itself does not specify the width. And I'm just saying, okay, assembler, go ahead and pick the right instruction for this one. But in this case, the assembler does have enough information to choose the width, because the width is already implied by the second operand, which is AL. $0 cannot indicate the width, okay? Because $0 can be an immediate byte, can be an immediate word, can be an immediate long. So an immediate operand does not indicate the actual width of the operand. But when you specify a register, AL definitely specifies an 8-bit register, and as such, compare itself can be implied to be compare byte in this case. So the B is not entirely necessary here, but I always make sure that I specify the width of the operation, unless I make a mistake or just forget about doing it. All right, so that part is done. And now we are down to here. At this point, I know that the P1 is already in AH. Yeah, in AH, because when we branch out of the conditional statement, well, do we know that? Yeah, we do. Okay, but without actually going through the math here, let's say that we do not. Okay, so if you're not sure, it is always okay to reload whatever P1 points to into AH first, and then use that to compare to whatever P2 points to. So I'm going to move byte. The first one is going to be indirect using ECX, which is our P1, into register AH. Then we have a compare byte instruction using %AH, which is whatever ECX points to or P1 points to, and compare that to whatever EDX points to, which is our P2, or whatever P2 points to. If they are not the same, J and Z, then we want to continue execution at the label called else if. Is that okay? So lines 76 to line 78 implements line 75 as a pseudo C code. Is that part okay? Okay, not okay? Okay, well, I'm assuming that means it's okay. All right, conclude the strings are equal. How do we indicate the strings are actually equal? Which register do we use and what value do we put into that register? 0 into EBX. Okay, so that's why I did not use EBX for anything, because I want to keep it for this purpose. But since this is actually the end of everything, I could have used EBX earlier, and it's okay to overwrite EBX at this point, because I don't need the counter nor the pointers anymore at this point. All right, so let's move on to this one. Same thing, so we get to this point, and to be safe, you can always just copy the byte over first, and then do the compare. So CMPB in this case, AH to, now this time the order of comparison is important. Before it's not, because when we compare for equal versus not equal, this is comparing for not equal to, it doesn't really matter, which one is the first operand and which one is the second operand, because not equal to is definitely commutative. You can switch sides without changing the meaning of the comparison. But when we're dealing with greater than or equal to, then it is important. The right-hand side becomes the first operand. So whatever P2 points to, or in this case, whatever EDX points to, becomes the first operand, and then whatever EAX points to, which is whatever whatever ECX points to, which is already in AH, becomes the second operand. This time it is important, unless you switch the conditional branch itself to flip the direction again. Okay, so we're looking at greater than or equal to. How do we express greater than or equal to as a conditional branch? Right? Okay, greater than or equal to means it is not less than, right? And we have two options here. It depends on whether chars are signed or not. JNB for unsigned, and JNL if we consider characters signed. It doesn't really matter. I'm not going to be tricky and use characters or ASCII codes beyond up 128. Because if I try to use the special characters beyond 128, then this becomes important. Are we treating the characters as signed or unsigned becomes important, okay? So here's a trivia that most of you should be able to answer. Is char signed in C and C++ or not? The answer is it is signed. Char is signed. If you want to compare characters all the way up to 255, you have to explicitly say unsigned char in a C, C++ program. The convention says that. I have no idea why they picked that as the standard, but just to be sure, let me consult the authority. Is char signed? And you can definitely tell that many people have asked that question, right? Okay, 4 answers. The book is wrong, great. The standard does not specify if plain char is signed or unsigned. In fact, the standard defines 3 distinct types: char, signed char, and unsigned char. If you pound include limits and look at char min, you will find that plain char is signed or unsigned. But even then, the 3 types are distinct as far as the standard is concerned. Okay, let's ask the other authority on this subject matter, which is obviously GCC, right? So let's go ahead and write like a very simple program. Okay, we just want to compare a character, single character. That's all we want to do. And we say int main char xy. And to understand whether it is actually signed or unsigned, we're going to do it this way. We'll say x is 0x7f, which is the last positive byte or positive value for a signed interpretation, and we'll make y 0xff, which is -1 when interpreted signed. Okay, and then we'll do a comparison and see where we go. Okay, so we'll say if x is less than y, without casting anything. Okay, we'll do one thing here. I don't know what we want to do. Okay. Else we'll say y equals y, which obviously doesn't do anything. It just gives the compiler something to do. I think the compiler is smart enough to figure out this is a null operation, so we'll see if we can trick it by saying this is not a null operation. This is actually meaningful. It does something useful. Okay. All right. So we'll go ahead and do a gcc -1all pedantic. I cannot specify optimization because the optimizer may actually get that code out of the way.
Busted.
Yeah. Okay. Warning: overflow in implicit constant conversion. So it is signed. Because FF is the last possible value for unsigned interpretation, which is 255. So the fact that it is complaining that y is out of the range is because y, which is a char, is actually signed. 7f is the last positive value that you should be able to specify. Now, to double confirm that this is actually the case, what we'll do is to say, okay, well, in that case, -1 as a character should be the same bit pattern. Okay, so see if this works. So the compiler should not complain in this case, because if it is signed, yeah, I mean, obviously -1 is within the range of an 8-bit number, and surely it is. Okay, so does everybody understand how I just verified, at least in the case of GCC, the way GCC implements the C standard is to consider char signed, which doesn't make a whole lot of sense to me, but that's the way it is. And that's why when you deal with something like this and you say, oh, I just need 8-bit to represent a number, and I want it to be signed or unsigned, don't trust char, okay? Because the standard seems to be kind of ambiguous about it. Use int 8_t and uint 8_t. Those are defined in standard stdint.h. And once you use those names, whether it's signed or not, and how wide the integer is, it's definitely determined. So you leave nothing up to the compiler to decide in that case. Any questions about this part? Nope. Okay. So now we can come back from the digression and go back to this point. So we'll use JNL, just to be consistent with the C code, because in C, chars are signed, so JNL is the signed version. If you use JNB, I'm not going to take any points off. It won't make any difference for the test cases, but it is kind of interesting to at least note that char is in fact signed. So when you use char, because you want to save some space as a counter or something like that, you have to remember you can only count up to 127 with char and not up to 255. That is where the difference where it makes a difference. All right, so JNL to the label else, and then the else branch has to conclude the first string is greater than the second one. Oh wait, I have to make the conclusion first. So if the first string is less than the second one, we're gonna move L $0 -1 into EBX to reflect that the first string is less than the second string. And then this is the last case here, which is basically moving a 1 into EBX. 1 becomes my exit code. So that should do the entire program, unless I make some stupid mistakes, which I do. So wow, it actually assembles. GDE, string, and compare. All right, so now we have to test the program. The way you test the program is you put a breakpoint into the program first, because if you try to change memory location without running the program first, it actually doesn't work. Okay, the debugger does not let you do something like that. So you put a breakpoint first, and then you run the program. When you stop, then you can set up the memory for comparison. I mean, for testing purposes, you can change this to like 4 and use .ask keys to initialize the string just for testing purposes. But I personally prefer to do it this way and use a script. If you understand how to write a script in GDB, that will actually make your process a whole lot faster, because you don't have to hand type everything. But in this case, I'm just going to hand type something here. I remember last time we already talked about how to use the trick of treating it as an integer, string 1 and string 2 as integers, so you can initialize 4 bytes at the same time. So now I'm using that trick here. So I would say string 1, consider that as an integer, and this time I'm going to spell out the string, but in a reverse order because of little endian ordering. So the last one is the null terminator, and then we have uppercase C, uppercase B, uppercase A, and then string 2 is the same thing. So the two strings should be considered the same in this case, and the program should exit with a code of 0, which is considered quote-unquote normal. So when GDB comes back, you should say, oh, the program exited normally. Yep.
With the fill max length, if you didn't specify the null terminator below, would it just roll on into the zeros up top as null terminators?
Say that again?
Well, string 1 up in the program, it's all zeros, right?
Yes.
And then if you did not specify the zeros below,
Yes,
would it just
it is
roll
already
in?
a 0.
Okay, so it
Yeah.
just roll into it?
Yeah.
Okay.
So we continue execution, exited normally, which means EBX has a value of 0 when it exited. Okay, well, let's go ahead and run the program again. This time we'll make sure that one string is greater than the other one. So one way to do it is simply to remove 1 byte from one string. So the first string is now just AB, and then the second string, oh, this is the second string, sorry about that. That's okay, we can still do the same thing here. So this time we make the first string ABC, the second string just AB. So the first string is now greater than the second string. It should exit with a code of 1. So we continue execution, exited with code 0, 1, which is great. Okay, that's exactly what we wanted to do. So now we test for the other case. We run the program again, stop at a breakpoint, and then we reset the memory here. So the string 1 itself becomes AB, and string 2 becomes ABC. Continue execution, and now it exits with code of 0377, which is the octal way of specifying a 16-bit -1. Octal means it's base 8, so each digit is representing 3 bits. 7 as 3 bits is 111. 7 as 3 bits is 111. 3 as 3 bits is 011. So we end up with basically 011, 111, 111. So that's only 8-bit. So the exit code is only 8-bit. That's kind of strange to me. But that's basically the correct exit code. Any questions about this part? So how do you test the program, when you want to test out, test it all the way up to the limit? One quick way to do it is to change max length to say 2 or 3, okay? So that way you can test the whole thing without having to spend like 20 minutes to initialize the 32 bytes of memory locations. You can also use .ask keys, okay, but change max length accordingly, so that way you can basically just shorten it for the comparison purposes. I can show you exactly what I mean by that, but if you do it this way, you have to remember to change the program back to what it was before you turn it in. So let's go ahead and do it. Well, we'll do the first way first. So if I do it the first way, I'm just going to change the max length here to 4. And I comment out the first line just to remind myself, what it was before, so I have a point to restore to. So once I have a program like this, I have to reassemble and relink, and then GDB the program again. Set up a breakpoint the same place, which is line 10. Run the program up to line 10, and this time I can now set var str1 to ABCD. Okay, so we have 0x44434241 and string 2 to exactly the same thing. So the two strings are now the same, but they're both at the limit. Okay, I'm only supposed to compare up to 4 bytes, and they're both exactly 4 bytes. The question is, are they the same or not? Okay, are they considered the same or not? But this is not going to test. This is not really a good test because all the bytes after these 4 bytes, they're all zeros anyway, right? So one thing you can do in this case is to specify the bytes after ABCD to be different. So if your algorithm is actually not working, it will catch one of those bytes and it will not come back and say that yes, they are the same. Yep.
Are there any bytes after those 4?
Yep.
Because when you change max length, doesn't that change?
Oh yeah, that is true. Okay. Well, okay. If the algorithm does not work, then it depends on what is after string 2. Okay, because the way memory is laid out is like this at this point, because max length is exactly what you are definitely right. So string 1 is referring to this byte. And because memory allocation is contiguous, so string 2 is here. But whatever is after string 2, these locations, we want to know what it is. Okay, we don't want to change it necessarily, but we want to know what it is. Because if the algorithm is not stopping at 4 and want to continue to compare more, then it will be considering this as the 5th byte of string 1 and this as the 5th byte of string 2. So as long as those 2 bytes are different, I can still test the algorithm for equality at the limit. Is that making any sense? So that means I just need to use the X command here to examine not 8 bytes but 9, okay? Because I need to know what is the byte after string 2. So B, we can use either C or X, doesn't matter which one we use. ampersand str1. So we can see that we have ABCD. These 4 bytes refer to string 1. ABCD refers to string 2. This is the byte right after string 2. Okay, it was not initialized by me. Okay, it's just floating there, because of whatever reason, but it is a 1. Okay, so if my algorithm is not working correctly and does not stop at the limit and is looking for a null terminator, it will definitely call string 1 to be greater than string 2 in this case, because it will consider this byte as the 5th byte of the first string. It will consider this byte as the 5th string of string 2, and the ASCII code of A, which is 65 in decimal, is greater than 1, which is the quote-unquote ASCII code of this byte here. Okay. So it will still be a good test. I just need to understand how memory is laid out first before I can say, okay, this is what we are predicting the algorithm should do, and it will still be a good test of whether it can compare at the limit. All right, so now that we have everything set up, we continue execution, and the program exits with code 01, so the algorithm is not working correctly, because it should come back with a code of 0. It should say that it compare, it's a code of 0, so it should come back and say the program exited normally instead of with a code 01. So that's exactly the reason why it didn't stop in time, basically. It did not stop when the length is at its limit. Or it stopped when the length is at the limit but came to the wrong conclusion. So it can be one of those 2 places that is causing the problem. And because of this, this is also a good opportunity to show you guys how to debug a program. I mean, how many classes actually show you how to debug a program? Very few, because all of your other professors are perfect programmers. They do not make mistakes. Unlike me, I make stupid mistakes here and there. I mean, that the point is not whether you make mistakes or not. The point is, can you fix the mistakes when you make one? Okay, we are all going to make mistakes. If you think that you can continue your streak of not making mistakes in your programs up to this point, you may be able to do it, which is great, okay? But I cannot do it, okay? I can write a 20-line program and have mistakes and I have to fix it. Okay, so the question now is, where do I look? It came to the wrong conclusion. So the first thing you do is go to the point where the conclusion is actually made, and then you trace your program backwards to see where the problem may come from. Is that making any sense? You don't start the program from line 1, you start from the last line where the conclusion was actually made. So the conclusion was made when I move a 1 into EBX. This is the part that actually put a 1 into EBX. So the question is, how do I get to this label else? I cannot be falling through because of the two cases, because there's an unconditional branch to make sure that we branch over the else branch here. So the only way to get to else is this JNL here. That's the only way I can get to the else branch. And doing this means I will be comparing whatever P1 points to whatever P2 points to, and if whatever P1 points to is greater than whatever P2 points to, I branch to the else case. Okay, great. Okay, that's exactly what is happening because I'm comparing 65, which is the ASCII code of A, with the ASCII code of 1. Okay, that makes sense. But how did I get here? How did I get to this point where the comparison was actually made? Well, I have to get to else if because of some reason, because this won't allow me to fall through. So I'm looking for a branch to else if, which is here. But there are, so there's one reason, this is one reason to branch to else if, and now the question is, okay, how did I get here? Okay. Once again, we're comparing whatever ECX points to with whatever EDX points to. If they're not equal, we branch to else if, but we know that already. We know they're not equal because one is greater than the other one from an earlier analysis. So that part is okay, we kind of understand how this will branch to else if, but how did I get to this point of line 77? Oh, this must be non-zero, right? Because if it was 0, I wouldn't be doing that. Okay, so if this is non-zero, we continue the branch. So how can this be non-zero? It means AL is non-zero when we perform the comparison, and that's why we did not branch to if continue to get to the continuation point, which is, here's my if continue, right here, which will conclude with a 0. Okay, so AL was non-zero. And if AL is non-zero, we go back and trace, what did we do with AL? This is the only part where AL was changed or decremented by 1. It's inside the loop body. And AL was initialized outside to 32. So this is a very bad mistake because I did not use max length here. Because when I change max length, that's the whole idea of using a label to indicate the width of something, so that I would use the label throughout the program, and then I broke my own rule and not use it. It goes like, oh, let's just hard code it to 32. Bad programming. So what have you guys learned?
Not to do that.
Not to do that. Very good. Okay, that is a very good conclusion. I'm not going to bring that up, but a thought just floated to my mind. I just have to kind of do the gate control and say, okay, let's not let it through. So, but the other thing that you can also see is how I trace the program's execution backwards. Okay, I started off with the observable symptom, which is EBX has a value of -1. How did they get a -1? here. How did I get here? Let's go backwards. How did I get to this label? Okay, well, there's no other way to get to this label unless there's a branch to this label. Okay, where is that conditional or unconditional branch? You look backwards and trace your way backward, and then we got back to the point where, oh, we figure out that AL is non-zero when we think it should be 0. Okay, and then we go look at, okay, how did we update AL? How could we have updated AL in the wrong way? Okay, you just look for all the instructions that can change AL. Subtract 1 cannot be wrong. Okay, that's easy. So the other part is the initialization, and we spotted it and go like, oh, okay, we changed the maximum length, but this is hard-coded to 32. That's why it's not working. But someone's going to say, well, did that actually fix the program? Because I can claim, all day long and say, oh, this is da 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 da, and that's da 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 da, and this will fix the program, and move on to something else, right? Well, let's go ahead and reassemble the program, relink it, and then test it again. And this is called regression testing. Regression testing means once you have identified a particular way to break your program, you remember that particular test case. So even after you fix that particular problem, you keep it in your repertoire of test cases so that in future, every time you make any change to the program, you retest with everything that was known to break your program before. Okay? And that's a very important thing to also utilize at work. All right, so we say GDB, string, and compare. Put a breakpoint on line 10, run the program, and then we set var str1 to 4, 4, 4, 4, 3, 4, 2, 4, 1. Yep, go ahead.
This is supposed to be str1.
Yep, string 1. Yep. And then string 2 to exactly the same thing. And then we continue execution. And this time it exits normally, which means it has an exit code of 0. Right. Any other questions? Yep.
How come with the exit code, why did they use octal?
That's a very good question.
It's like the least useful base.
But probably historically it's used. Okay, so you can say y GDB exit code in octal, right? I mean, you can just ask any question, and somebody has an answer. Whether the answer is correct or not is a whole different question, right?
They wouldn't have it on the internet if it was wrong.
Well, this is the argument for crowdsourcing, because if someone posted something that is wrong, crowdsourcing means other people. You rely on the crowd to criticize the wrong answer and point out the correct one, which works sometimes. Okay. So answer. Oh, this is also useful. The dollar question mark is the shell value of return value. That's one way to test your program when you run it on the command line. You can actually do it that way too. The octal representation eases the interpretation of the exit code for small values. Blah 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 blah. That's not the right answer. If an application terminals abnormally, its exit code is octal 200 plus status. So that was a poor man's error message. It still doesn't explain why they picked the base octal instead of hexadecimal, which would actually make more sense.
Because they're poor.
Hmm?
You said it was a poor man's. So because they're poor? Fair enough.
Okay. But octal is not any poorer than hexadecimal.
Poor thinking.
Well, it depends on how you read this message. Is it poor man's error message or a poor man's error message? Yep. Is it right associative or left associative?
We need to have an English major.
Then I'll use a lot of parentheses.
Yeah. And or.
Yep. All right, so there's the answer of this particular homework assignment. Did you guys find this particular homework assignment challenging? If so, in which way was it challenging?
It was converting the logic into assembly.
So
Which conditional jumps do we use? Which direction is the comparison going?
So there's a lot of detail to deal with, right? Now, if you do the flattening completely in C first, you can actually debug the program and test it for every step that you take to flatten the program. So that would probably help a little bit compared to like doing what I just did, going straight from C to assembly. And that's why I recommended you guys to start with a C program completely in C and using structure code, and just do the flattening part one step at a time, and then retest your program after each step to make sure that each translation does not introduce a logic error into the program. Any other feedback? Yep.
I actually found this one more straightforward than the last couple.
The treasure hunting ones?
Yeah.
I know.
Because this is less abstract, I guess.
Well, this one is, it gives you more degrees of freedom in a way, because you can, it's just putting pieces together to do something, whereas the other one is very restrictive. It's like, okay, put something in place of the question mark and make it do this, right? So the other one is more like solving a puzzle. This one is more synthesis. You're actually putting something together to solve a particular problem. So it depends on your thinking process. Some people think in a certain way, and you'll find certain things are more challenging than others. It also depends on whether you you have a bug in the program that is difficult to spot. Okay, there are many places where you can put a bug here that can be difficult to spot, like not putting a $ for immediate operand and you accidentally use direct operand instead. That one is not too bad in this program, because for the most part you're dealing with zeros and ones as constants, and as such, the program would crash right away on the instruction that actually has a problem. So that should not be as big of an issue. A more nasty issue with this type of program is using the wrong width for comparing. So to compare byte, if you use a compare word or something like that, the program may appear to work for some cases, but it won't work for all cases. You guys want to see how a program may seem to work when it has a wrong compare width? Sure. That seems kind of hesitant. All right, so what I want to do is to just pick one of the compare byte instructions, and this is not the one. Okay, comparing the width or the length is not the issue, but every time you compare the bytes pointed to by P1 and P2, that can be an issue. Like if this one, if people use the wrong width and change the instruction before to also use the wrong width, like if this is a W or L, it can break a program in a very nasty way, because if you use a very short string, it won't show up. It will still compare quote unquote just fine. But when you make the string longer, then it will have an issue. Okay, especially when one string's end is actually becomes the beginning of the next string when the width is not interpreted correctly. So, so those are the things I'm going to check for, is to initialize the strings long enough so that these problems will start to pop up. Any questions about this part? Nope. All right. So if there are no questions, we have about 10 minutes left, which is really not a bad time, because we are just about to begin the discussion of operating system interface. How does a program talk to the operating system? And for the most part, the first part of this discussion is not specific to assembly language programming, and it is certainly not specific to the i386 architecture. So this is the slide that talks about this part. And it's really hard to ask questions about this one, because it is really just more of a theoretical discussion than actual stuff that we can be tested on. But it is also important to understand all this stuff. So we start with section 2, which is describing life without internet. And the way I'm not going to read my own notes here, but this is where you can find the notes for this particular section. So I encourage you guys to read this part here, after today's lecture or before the next lecture. Life before without interrupts is DOS, MS-DOS, Microsoft DOS, disk operating system, and most operating systems in that era do not make use of interrupts. What does that mean? Now, how many people still remember the DOS prompt, C:, and then the greater than symbol? Okay, that's the only way for you to interact with an IBM PC, back in those days. So the question is, when you press a key, what is really happening? How does the computer understand that you just type the key? Let's say you want to do a DIR, so you press D, press the D key, and then you release the D key, and then magically, the letter D appears on the screen. So the operating system somehow registers that you just type D on the keyboard. How does that happen? Any idea?
Asks the keyboard if there's any key presses every clock cycle.
Yep. So DOS, not using the feature of interrupt, is basically constantly polling the keyboard controller. In other words, inside the keyboard, okay, I'm just gonna, inside the keyboard is a keyboard controller. The keyboard controller is a very primitive processor. Its only job is to scan the keys and see if anything is pressed and if anything is released. Okay, so a key press and a key release are both considered events. Okay, and the keyboard controller can remember up to a certain number of events. Okay, in case the processor is busy doing something else, it can actually remember a certain number of these keyboard events. In the DOS days, what a PC would do is it will constantly ask the keyboard, do you have a key press event for me? Do you have a key press event for me? Do you have a key press event for me? Do you have a key press event for me? Do you have a key press event for me? And so on. Okay, you guys get the idea, right? So when you actually press a key, then the keyboard will come back with an answer. Yes, we have a key press event. And then DOS will go ahead and ask the keyboard controller and say, okay, which keyboard event are we talking about? Oh, this key at this location is pressed. And then the PC, the operating system, will look up the key map and find out, okay, based on a US keyboard, based on the configuration of the keyboard, that location maps to lowercase d at this point because the state of the caps lock is off and so on and so forth. And then the register, and then the operating system will register, okay, you just type lowercase d. All right? And then right after that, what do you think the operating system continues to do? The same thing, by polling the keyboard again, okay? Do you have a key for me? 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 Okay? Now, when your operating system is not multi-user and not even multi-processing, you cannot run multiple programs at the same time, this is a non-issue, right? Who cares? I mean, But what happens when we switch from DOS to Windows 3.1? What is Windows? How is Windows different from DOS? Not only from the GUI versus the text user interaction mode is concerned, but from the multi-processing point of view, how are they different? In DOS, can you run multiple programs at the same time? Like I want to run Lotus 123 and WordStar at the same time? Nope, cannot. Okay, you can run one program at a time, and that's it. Okay. But what about Windows? What is one of the features that Microsoft touted when they released Windows 3.1, which was not a bad product back in those days? You can run multiple programs at the same time. Okay, so you can run Microsoft Word on one side, and then you can have Notepad running on the other side, and they can run Quotico at the same time. But back in those days, so-called running at the same time relies on cooperation between the programs, which means Microsoft Word is written in a way that has that has what we call a yield statement sprinkled around the entire program. So at various points of that program, Microsoft Word will say, okay, I'm voluntarily giving up control so that Windows can pass control to the next available program to do some processing. Notepad would grab the control and say, oh, I am the next program. And Notepad would do its own thing. Okay, maybe blink the cursor or allow you to type some keys or do something. And then when it's done, it will pass control back to the operating system, Windows, and say, okay, I'm done here. Let somebody else have control and do something. And if you open up a DOS prompt, what happens? When you open up a DOS prompt in Windows 3.1, the DOS prompt will do what a DOS prompt usually does. And what does it do? Hey keyboard, you got something for me? 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 What about that cooperating kind of thing? There's none. And that's why, back in those days, when you open up a DOS prompt, say goodbye to multiprocessing, because there's no multiprocessing at that point. All right, is that okay so far? Okay, now fast forwarding how many years? 85, 82 or so to 2014, so 30 years, and I'm old. So fast forwarding 30 years, and now you have your fancy, smanchy mobile device. Come on. And just think about your, iPhone or Android or Windows, mobile device, and think about, what it's doing at this point. Okay, I have to press this button to kind of wake it up to do something, right? So what if we are using the same approach as before? In other words, the Android or iOS or Windows is constantly polling the hardware and say, hey, is this button pressed? Hey, is this button pressed? Hey, is this button pressed? And do it 2 billion times per second. What would happen first? You would notice the device warming up, heating up, it would get hot, and then the battery would go dead. Right? Because your processor is spending all that time, all the processing power doing just that. Is this button pressed? Is this button pressed? Is this button pressed? Is this button pressed? And out of the 2 billion times per second, and 2 times what, 3,600 per hour? Okay, 2 billion times 3,600, that would be the number of times that it would poll per hour. How many times would you actually be pressing that button? Maybe once, maybe twice, maybe 3 or 4 times, right? So what happened to all the other polling cycles? They're all wasted, right? They just turn into heat, and you have to charge your cell phone every 5 minutes, or keep it pressed to charge all the time. And the USB controller will say, "I cannot supply that much current. Sorry," right? So what is a better approach? Instead of having the processor to keep asking, do you have something for me? Do you have something for me? Do you have something for me? What would be a better approach to solve this problem? Either from the button perspective here, the touch screen, or the keyboard, or your mouse, what would be a better approach?
Give a command. Instead of asking, just give it.
Okay, who is giving whom a command?
Like the button. So I press this.
So the device, the keyboard, or the button, or the touch screen would initiate the conversation, not having the processor to ask constant, right? That's exactly what it is. That's the concept of interrupt. So the next question is, if the keyboard is the one that is initiating the connection and say that, hey, somebody just press a key, can you do something about it, operating system? What else is the operating system doing? In other words, when you're not using your mobile device, it's not off, right? Most of you keep your mobile devices on, the whole time. So what is it doing? For the most part, it is quote-unquote sleeping. Okay, it's in a low power mode. It is actually sleeping and conserve power. But it does wake up from time to time to check on things, right? It has to check on various things, network communication and whatnot. So what if during a network communication, you press this key here? So the controller, the hardware controller is saying, oh, you know what, we have an event here. Somebody just pressed the power button. But your computer, the operating system, is actually doing something at a time. So what do you think should happen here? Okay, I'll give you 2 options. One is, the operating system will finish whatever it was doing entirely, like if it's downloading or installing a new app or updating an app, it will finish updating the app first, and then we get to a certain convenient point and say, okay, now I'm free, let's see here. Oh, power button, you got something for me, let me process it. That's the first option. The second option is the operating system. I know, it's really mesmerizing, right? So the second option is at the instruction boundary, the power button is going to tell the processor and say, hey, I got something here. Someone needs to process this event here. And then the processor will go ahead and do whatever is necessary when the power button is pressed, and then go back to finish up the installation of the app or the update of the app. So option A or option B? Option B makes more sense, right? Because otherwise, when you press the power button, you might have to wait for a half second or something or longer for an app to get updated first, right? Which is not acceptable. That is the concept of interrupting, because in this case, the power button is interrupting the operating system, and the operating system will go do whatever needs to be done, and then come back and continue to do whatever was interrupted. Yes?
How does that handle threaded processing?
Threaded processing, okay, in which way? Because threaded processing can be impacted by interrupts in several ways. So are you talking about timer interrupts or multi-threading like time slicing? Or are you referring to?
So instead of interrupting the entire processing stream, could you just interrupt a single core, single thread?
Okay, that's a good question. When you're interrupting the entire system. So you're not applying that to a single thread. You're actually applying to the entire system. For a protected operating system like Linux or Windows NT or Mac OS 10, what happens is the operating system is responsible to deal with interrupts. So whatever the computer is doing at that time, it can be a user process. Okay, it can be your application running with whatever number of threads and whatnot. But the operating system is in charge of dealing with the interrupt. Now, in the case of a multi-core setting, one of the cores will have to deal with it. Okay. Now, whether the other cores can continue to do whatever in parallel of whatever they're doing is a good question. I do not have the answer to that, because if they can continue to do whatever they are doing, that can cause issues too. And the answer, I have no answer to that question. With a single core situation, the processor will basically put down whatever it was doing before, handle the interrupt, and then come back and continue from where it was interrupted and continue from that point on. With a parallel core, like a quad-core processor, it is a good question. I have to look it up and find out exactly how it is handled. Because I can see problems when you allow only one of the 4 cores to handle the interrupt, and then the other 3 cores to basically continue to do whatever they were doing continuously without getting interrupted. Because certain interrupts can communicate with other programs using variables. So if you allow other things to be happening at exactly the same time, then you can have an issue of a thread is using a variable that is already quote-unquote modified by the interrupt surface routine. So that's a very good question. I have to look it up. But the general concept is just basically, you generate an event whenever the hardware thinks, oh, okay, I need some attention here. And then the operating system will intercept the interrupt, do whatever the interrupt needs to do to handle the hardware source of the issue, and then come back to continue to perform whatever was interrupted in the first place. That's the general concept of interrupting. So we are just starting out with section 2 and a little bit of section 3 at this point. And then we'll move on to section 4, 5, and 6. I'm not sure about that. So we'll definitely get to 4 and 5 in the next class. So you might want to read ahead of me just to know what kind of terminology we'll be talking about. All right. So there are no actual homework assignment today, so I'm letting you guys take a short break because we don't have any new concepts, for a new homework assignment. But by Thursday, we would have done enough with operating system concepts, so we'll have a new homework assignment on Thursday. And you can tell the, well, I guess, never mind, I'm gonna tell Mr. Fox. We took a little bit longer than usual.
Oh, wow.
You get your